All right, gentlemen, good morning. Let's take a look at solving quadratic trig equations. So yesterday, or last class, we looked at solving linear ones, and now we're going to review that and then move on to quadratic trig equations. All right, so let's start with a review from last class. Just as we saw from Dr. Summers, we want to isolate the trig function first, and then we find the angle theta that gives us that ratio that we're given. Okay, so some review. First, let's look at the range we're looking for. All right, so this is negative pi over 2 to pi over 2. So that is in quadrant 1 and quadrant 4. Okay, so we're looking at anything in this range right here. Okay, now let's take a look at our function. What do we have over here? So we want to get the function by itself, the trig function by itself. Sine of theta we want to be alone. So we treat it just as an x, where we move everything away from that. So we get sine of theta, or as if it were an x, equal to something. So we subtract radical 3 from both sides, and we get negative radical 3. Then we divide both sides by negative 2. Again, just as if that sine of theta were an x, we treat it as something we're trying to get totally by itself. Okay, so this is what we have. Move the radical 3 over, divide both sides by negative 2, and now I have a positive radical 3 over 2. Okay, so now, just as a review, this would be the same thing as if I were to say arc sine of radical 3 over 2 is equal to theta. Right there, identical. We had said that, this, or sometimes we even see it as this with the little negative 1. Right, how these are the same, and we're getting a theta from each of them. It's all the same idea, and the same question remains from all three of these. What angle do I need to get me this? So I want to look here. This is positive. I see that this is positive, so that tells me I'm in quadrant 1. So I'm going to draw my little reference triangle in quadrant 1, and it's going to help me know what my angle is. So here's my angle, theta. My opposite, because it's sine, is radical 3. My hypotenuse is 2. Pretty easy at this point to know that's 60 degrees. So 60 degrees is pi over 3, and there is my answer in radians, pi over 3. Okay, I'm inside my range, which is good. If I were negative, I'd be down here. This is positive, so I would normally say I could also be in quadrant 2, but that's not in my range, so I can't be in quadrant 2. I can only be in quadrant 1. Okay, do the next one. The next one we have secant. Again, this is what I'm trying to get by itself. I'm isolating the secant of theta. First, I take a look at my range I'm looking to be inside, and it's 0 to pi. So now I'm either in quadrant 1 or in quadrant 2, somewhere in here. Okay. I want to isolate the secant, so I subtract 7 from both sides, get rid of the adding or subtracting thing, so I have a negative 8. I have a 4 in front, so I want to divide both sides by 4, and I get secant of theta is equal to negative 2. Okay, I have isolated my secant. Again, we saw that this is the same as arc secant of negative 2 is equal to theta. Or this is the same as secant negative 1 of negative 2 is equal to theta. And we know that. The other thing we know from this is, which is kind of beneficial, is secant of theta is 1 over cosine of theta. So over the past couple of weeks, we've kind of gotten the handle on reciprocals and the inner workings of trig. We're going to use a lot of these in the coming classes when we do trig identities. So we got to get pretty good at being able to see a function and being able to flip it to its reciprocal or change it to something else. So just to kind of get a handle on that now, we know secant of theta is negative 2 is the same as this, Technically, I could also view this as, well, what's the reciprocal of secant? That would be cosine, right? So 1 over secant is cosine, just like secant is 1 over cosine. If I do that, I want to view this as cosine. Instead of writing secant equal to negative 2, I'd write cosine is equal to negative 1 over 2. If I flip secant to be cosine, I have to flip the negative 2 to be a negative 1 over 2. I like to do that. It's easier for me. If you want to leave it as secant, that's fine. I'll show you. You get the same answer either way. Again, just as we saw before, I can view this as arc cosine of -1/2 is theta, or cosine to the -1 of -1/2 is theta. All are the same. Everything in purple is saying the same thing. Everything in red and blue, these are saying the same thing. And really, all of these are saying the same thing. As long as I've flipped it correctly, these are all exactly the same. So hopefully that's a little helpful. Now, okay, so this is negative. Negative tells me I'm in quadrant 2. How do I know I'm in quadrant 2? Well, all students take calculus. Everything, this is only sine, and this is secant or cosine, so it's not positive, so I got to be in quadrant 2. So I'm going to draw my triangle as if I'm in quadrant 2. There we go. Here's my theta. Right? So you can view it two ways. One way would be, well, secant is hypotenuse over opposite, and this is 2 or 2 over 1. Or I can say cosine, which is adjacent over hypotenuse, and that's 1 over 2. The negative just tells me what quadrant I'm in. So either way you look at it, h over a is 2 over 1, or a over h is 1 over 2. It's the same thing. So my hypotenuse is 2, my adjacent is 1. That tells me that this is a radical 3, which means this angle is, I'm going to draw it over here, 60 degrees. Now the key thing to keep in mind, so I'm going to take this whole thing, a little bit more space. The key thing to keep in mind, now that I've determined that that's 60 degrees, is I'm in quadrant 2 though. In quadrant 2. So it's not 60, but it's actually from here all the way till I get to 60. So what would this angle be? This is my answer. What is that angle? That's 120 degrees. Because this is really, that 60 in quadrant 2 is really like my reference angle. So if I know that that's 120, how do I change that to radians? 2 pi over 3 is my answer to the second one. 2 pi over 3 is the answer to my second one. And the key at that was, because I was in quadrant 2 and I found it to be 60, it really means I'm 120. Okay, cosine is negative. It's got to be in quadrant 2 because it's in my range over here. It can't be in quadrant 3 because it's outside of this range. It's negative, so it's got to be here or here, locked into being there. All right, let's look at the third one, and then we'll go on to some new stuff. Again, we have this right here, which tells us our range of values we're looking for is either in quadrant 1 or in quadrant 4. So I'm somewhere over here. Okay. Now again, we're solving, so we get our cosecant by itself. Very simple to start. Cosecant of theta is 1. Okay. Just as we've seen, I'm going to write it again. Cosecant of theta, that would be the same thing as if I would say arc cosecant of 1 is theta. Right, so those are the same. We wrote that a couple times. If we want to see how to change this into, and I'll write it like this too, cosecant of -1 of 1 is theta. We also can write this as sine, right? So again, because sine is 1 over, I'll write it the other way, because cosecant of theta is 1 over sine of theta, right? If we flip cosecant to be sine, we got to flip our +1, but very nice, 1 over 1 is just 1 over 1 flipped. They're the same. So I can write this. I can write arc sine of 1 is theta, or I can write sine of -1 of 1 is theta. So again, all of these, all 6 of these are the same. Or we want to get a good understanding of what is equivalent. Cosecant is 1 over sine. So if I wanted to flip this, sine is a little bit easier. If I don't, it doesn't really matter. I can leave it as cosecant. I would say for this one, because it's an easy flip, I would flip it and look at it as from the point of view of sine. It doesn't really matter. Now I got 1. 1 tells me I'm a quadrantal. Right? Whenever we got 1 or 0 for sine and cosine, those were quadrantals. And remember, sine is the y. Right? So it's an ordered pair, x comma y. So if I look at my unit circle, I'm up here, I'm over here, I'm over here, I'm over here. Where is y equal to 1? Up top here would be exactly where I'm equal to 1. Over here, that's if I'm 1 comma 0. This is -1 comma 0, so that's when sine is 0. This is 0 comma -1, that's when sine is -1, and this is when sine is 1. So we have our little unit circle. We remember quadrantals. We did that a while ago, but whenever I get 1 or 0 for sine or cosine, I'm looking at a quadrantal. All right, so I'm all the way at the top. Can I be all the way up here? Is that allowed? Yes, because I am less than or equal to. So my answer is 90 degrees or pi over 2. There's my answer. Okay, so hopefully that was a nice review of the last couple classes. We did a little bit of quadrantals. We kind of viewed our reference angles in the second one. We looked at the stuff we did last class in all three of these, and our inverses are still pretty new to us. Okay, so now let's start to look at our quadratic trig equations. This is when we saw quadratic in the second trimester. Quadratic always meant there was two answers, because it was something like x squared. Right, so it was either a parabola that looked like this, a parabola like that, or it was a parabola like this. But either way, it had two x-intercepts, right? Two solutions. Those are quadratics. And then x to the third had three solutions. X to the fourth had four, unless it was a double root or something like that. All right, so let's do a couple of these. We're going to take these nice and slow, but basically we treat them just as we always did with quadratic equations. We want to solve them as we normally do, and we're going to get two inverse trig functions to solve. Okay, so first we'll look at this from the point of view of only -pi over 2 to pi over 2. Here's my little graph. Again, just as we saw in the ranges up above, that's in this range. -90 to +90. Okay, what we're going to do is replace sine with x. Right, so everywhere you see, it's almost like a composition, right, where you're like replacing. So everywhere we see a sine, we're going to write an x. Sine squared of theta means x squared, and sine of theta means x. Right, so this is a quadratic. It's something, an a value, a number, a coefficient, times something squared, sine squared, plus a 1 times an x-like thing, and then a c value. So we replace my sine and my sine squared with x and x squared, I get this. Here's my sine squared, and there's my sine. And now this second equation is something we definitely have seen before. Something we saw when we were doing factoring in the beginning of the year. So it should be pretty straightforward to follow. There we go. I now have moved everything to one side. I'm looking for two numbers that multiply to -2 and add to +1. Right, my AC. And to do this, I get 2 -1. Right, because I got to add to +1. So when I do that, very simple, 2x squared plus 2x minus 1x minus 1 equals 0. Take out a GCF of the left side. Take out a GCF of the right side to get those parentheses to match. 2x minus 1 and x plus 1 equals 0. Okay, so that factoring should come relatively easily to us. Okay, now at this point, you can do two things. Oops, one moment, there we go. You can kind of do two things here. I'm going to kind of write them side by side. You can either solve it, right? What did we do here? We solved it. And we would get 2x is equal to 1, and x is equal to 1/2. And this would give us -1. That's what we used to do. Same idea, right? You can replace it to sine theta minus 1 and sine theta plus 1. Right, so all I did was I replaced sine squared with x squared and sine of theta with x. Got down to the bottom, got to here. I can either get my answers and then replace it, or replace it and then get my answers later. So you're going to get the same thing, you'll see. Right, but if I solve this, I get 2 sine theta minus 1 equals 0, and sine theta plus 1 equals 0. Just like we did here, where we set each factor equal to 0, we're doing the exact same thing. Sine of theta equals -1. Sine of theta is equal to 1/2. If I were to have replaced at the end, I would get the same thing, right? If I solve and then replace, or replace and then solve, I get the same thing, right? So either which way we look at it, that's our answers, 1/2 and -1. So whichever way works better for you. Generally, we write it like this because sometimes there's a little bit of tricks that this help with, but we'll see. Okay, now we have two answers. We have to do exactly what we do up here for two different linear equations. One of them is 1/2 and one of them is -1/2. Oh, I'm sorry, -1. This is positive, so this tells me I'm in quadrant 1. So I'm going to draw my little triangle. In first one, theta, 1 and 2. That's this one. Right? And that's very easy to tell. We are opposite is 1, hypotenuse is 2. So this has to be 30 degrees or pi/6. So that's one answer. Okay, and now we have a second one. I'll do that in purple. -1. Oh, here's another quadrantal. It's a 1 or -1 value, right? Or 0. Right, if we look at our unit circle, up here, down here, over here, sign is y. So when is y -1? That's down here. Y is -1 down there. So my other answer is whatever's down here, the very, very bottom. Can I do that? Yes, because I am less than greater than or equal to pi/2, -pi/2. So my answer of -90 or -pi/2 is my second answer. So we have two answers here, pi/6 and -pi/2, or -90 and 30. Those are our two answers here. Okay? So it's exactly like solving a quadratic equation, except we have to do at the end what we had done above twice. Okay. So let's look at the next one. Tangent and cotangent. Okay. Here's my range of values I'm looking for. -pi/2 to pi/2, so quadrant 1 and quadrant 4, somewhere in this area. Okay, so we first start to write this, and we think, okay, well, where's the something squared, right? Up here, I had sine squared and sine, so it was pretty easy to see it's x squared and x. I don't have that here. True, you're right. What do I know? I have tangent of theta. What do I know about cotangent of theta? What do I know about cotangent of theta? Well, that's the same thing as 1 over tangent of theta. So I'm replacing cotangent with 1 over tangent. Why did I do that? Why do I do that? Because I want one trig function. It would be like me telling you to solve x plus y equals 3. That's it. You can't solve x plus y equals 3. How do you solve this? You're not going to get an answer. All right, so the same idea, we want to make it so it's one trig function. So that's why we got to remember our reciprocals so we can match our functions really nicely. Okay, tangent and 1 over tangent. So now I got two things with x's in them, essentially. Now the one thing is, what do we do here? I have a tangent, and I have a 1 over tangent. Just as we saw in the midway, a little bit later than midway part of the second trimester, if I have like solving rational equations, right, where we had x's and fractions, if I multiply the entire equation by tangent of theta, in other words, I can find my common denominator and multiply it throughout, or my only denominator is tangent, or 1, or 1. So if I multiply by tangent of theta, I'm going to get tangent squared of theta. Tangent times 1 over tangent is just a plain old 1. That cancels, very nice. And then equals 2 tangent of theta. Okay, so just like if I had, it's very similar to if I were to have x plus 1 over x is equal to 2. And you multiply everything by x and it gets rid of the x on the bottom. So now you have something without fractions. All right, so just as we saw before, I'm going to say x is tangent of theta, and x squared is tangent squared of theta, just as we saw up above. So here's x squared plus 1 is equal to 2x. I replaced my x's with tangents, and I replaced my x squared and tangent squared. Solving this, again, should be pretty easy once we replace it with x's. Okay, now two numbers that multiply to 1, positive, and add to negative 2. Well, it's nice. We have basically dots, or not dots. We have two of the same factors. So x minus 1 and x minus 1. So it's like a double root. Okay, and so now we can just replace this with tangent of theta minus 1 is equal to 0, and we replace it back with tangent of theta minus 1 is equal to 0. Tangent of theta equals 1. We get the same thing over here. Tangent of theta equals 1. So what is that? What angle for theta would give me 1? Well, with tangent, right, we know that to be 45 degrees. we can do it like this. So we're positive, so I'm in quadrant 1, because I'm positive. 1 and 1. Right? We've seen this as an isosceles right triangle, so it's 1 over radical 2 is if it's sine of 45 or cosine of 45. So this is 45 degrees, or pi over 4 is my answer. Right? I got it twice, but pi over 4 twice. It's like a double root. Okay, so there is our solution, pi over 4. Okay, so there's our second one. We're going to do 2 more, and then we'll give you some classwork. Okay, so we have another one with sine squared. Here's my range I'm looking at. I'll do this up here. Seen this a couple times now, quadrant 1 or quadrant 4, so I'm somewhere over here. Sine squared of theta, I'm going to make that x squared. Sine of theta, I'm going to make that x. Okay, so at this point, we hopefully are getting the hang of that. Okay, so may have to do some manipulating, but I got to make it a quadratic, which we did. Now we solve. Okay. Two numbers that multiply to negative 2 and add to negative 1. X minus 2. Whoops. Yeah, I can do it like that. X plus 1 is equal to 0. Very nice. There was no a value. There was no a value, so I didn't have to do my longer, splitting it up AC method. I'm kind of able to just jump down to this. Okay. So now, very simple. Sine of theta minus 2 is equal to 0, and sine of theta plus 1 is equal to 0. I replace my sine with x's, and I get sine of theta is equal to 2, and sine of theta is equal to negative 1. Right, so we look at this and we say, well, wait a second. I have never seen this. Sine of theta is equal to 2. It's never larger than 2, right? It can be 1/2, or radical 2 over 2, which is less than 1. Radical 3 over 2, which is less than 1. Or it could be 1, right? Think of the unit circle. It's never more than 2. So this is just too big. So no, we don't use. It's out of the range. It never happens. This can never happen. It's kind of like an extraneous root when we had those numbers we just threw out. So if you get something larger than 1, you can't do it, right? Think of our domain of all my arcs, right? Of arc sine and arc cosine and everything. It's negative 1 to 1. So that's outside of it. I can't do it. Negative 1, though, this I can do. Just as we've seen a couple times now, it's a quadrantal. Sine is my y value. Which one of these is going to give me a y value of negative 1? That's down here. Can I use that part? Yes, I can, because it is less than or equal to pi over 2. Or negative pi over 2, rather. So my answer here is negative 90 degrees, or negative pi over 2 is my answer. Okay, so there's that one, negative pi over 2. Right, so we keep in mind we cannot be outside of our domain, our area, right? So I cannot use that one with a 2 because it's too big. All right, let's look at our last one. We have a new range now. between 0 and 2 pi. So this one's a little different. We can use any part of my coordinate plane, right? Anything. I can use any part over here. Okay, so now we're going to have a couple answers here. This one's weird. Now we got sine and cosine and a cosine. Does sine turn into cosine? No, right? There's no like sine is not 1 over cosine. No, that's for cosecant. What about cosine turning into sine? No, cosine turns into 1 over secant. Those match up. We're going to learn some little tricks with like sine squared and cosine squared, like double angle formulas and Pythagorean identities with sine and cosine, and all that exciting stuff is yet to come. But for now, we haven't seen this. So let's take this nice and slow. So all right, so we got this, our coordinate plane, and we have this. It's hard, right? Because we can't, like, are we going to replace sine with x and cosine with y? You're going to have two variables then. You could do that, but it's still going to get a little bit weird. So let's do this something different here. Let's try to move things around and get everything on one side. So I'm going to move this over. Sine of theta, cosine of theta, minus cosine of theta. So if you wanted to make it x and y, I'll kind of write that down below here. And if you make it x and y equals y, right? Mentally view it like that. Right, this is kind of like when we did inverses. It's really similar. X, y minus y equals 0. That's kind of what we have up here, equals 0. When we had inverses, right, we had to solve this. We took out a GCF of a y and was left with x minus 1. And we were able to solve, right? It's just like we saw with inverses. When we have two variables, we take that out as a GCF, and I'm left with x minus 1, the coefficients. Same thing, there's two cosines here, one sine. So if I take out a GCF of cosine of theta, I'm left with sine of theta, my coefficient of cosine. The x is the coefficient of the y. What is the coefficient of this? If I take out a cosine, what am I left with? If I take out a y from here, what am I left with? A 1. And obviously the sign stays the same. This 1, this negative stays the same. Okay, so now you look at this and you say, well, now what? Right? Technically, I can set each of these equal to 0. I've technically factored this. Right? I factor this into two things that multiply and give me 0. Two things that multiply and give me 0. So based on my 0 product property, I can set each of them equal to 0 to solve. Okay, so now when is cosine 0 and when is sine 1? Well, if we think about again, we got zeros and ones here, so very nice. We can look at both of those are quadrantals. So let's look at our unit circle. Very nice. We can use any part of our unit circle. There's no restrictions here. Okay, when is cosine 0? So again, cosine is my x part and sine is my y part on this unit circle for the unit circle. Okay, so this is, I'll label my points. This is 1, 0, 0, 1, -1, 0, and 0, -1. Okay, cosine being my x values. When is x equal to 0? There and there. So cosine, I have two answers here for cosine. Cosine of theta equals 0. What 2 points does it equal to 0 at? Well, at all the way up, pi over 2, and negative pi over 2. Those are the two spots when cosine is equal to 0. When is sine equal to 1, which is the y part? It equals 1 here, and that's it, just up there. So sine of theta is equal to 1 at what point? At pi over 2. So a little bit of a weird example, right? But you get pi over 2 twice, and you get a negative pi over 2 in there. And this was nice because it was just quadrantal. So we only really had 4 options. We drew our unit circle, no restrictions. We could use any part of it. And we knew that sine is my y values of my quadrantals, and cosine is my x values, which were 0. Okay, so looking at all those, right, if we just take a zoom out, right, we try to do one of each, right, kind of a simple one with sine, normal. One we have to replace tangent with its reciprocal. This one where you have a number you can't use, and then this one with sine and cosine, that you have to kind of, you get two answers, one with sine, one with cosine. Okay, so there's a lot to take in there. Watch this video a couple times if you need. You have 6 problems for homework. Right, and just keep in mind of your ranges and draw your little reference triangles and make sure you know which quadrant you're in.